My brave survivors. You didn't want to play outside? We talked all about how you don't need to know anything about what's under the hood of these things. It's raining! I am ever so slightly more entertaining than being stuck in the rain. That's good. As long as I can maintain that, everything, all is well. So let's open this black box then and have a look at how some of these things go. So we've already looked at linear regression. I moved it earlier in our menu. And now we'll go through in this order, and we'll just get a taste, we'll just get a flavor. So as with regression, we don't go into the nitty-gritty, because I leave that for homework for you. Enjoy the code, enjoy the textbooks. We're just going to get like a feel for it together very quickly. So, first things first. Clustering. In a nutshell, this is about birds of a feather flocking together. Our example algorithm that we will look at is k-means, and we've already seen this idea earlier in the course. Here are some photographs, and then we said put like things with like, and our clustering algorithm made two clusters based on cat 1 and cat 2, or maybe based on is the tongue sticking out, or is the tongue not sticking out, sitting, standing, cat selfie, not cat selfie, or what have you. That's clustering algorithms. So, for our example, do you see any clusters here? I see some clusters by eye, sure, something like that, yeah? Okay. Could we have done this without having labels? That is a trick question to see if you are paying attention. There are no labels here. So, of course, this is unsupervised learning. All we know about is the ingredients, and we are finding those clusters ourselves. Could we have done this without using our eyes? Sure, otherwise what are we doing in this section? So, welcome to k-means. The K in k-means stands for the number of clusters that you are requesting. So this is up to you when you are using the algorithm. You are ordering as if from a menu, I would like 3 clusters, please, or I would like 2 clusters, please. That's the K. What about means? The means are something like centers of mass or gravity. So don't worry about what the math is behind centers. Just think of that kind of as a center of gravity. And your intuition for it will be pretty good, actually. I'll be computing them for you, but I'll be having you guess first where it's going to be, and you'll notice that you'll get the hang very quickly of what this object means. So the technique begins by sprinkling some labels throughout our data entirely at random. Boom. We have a blue cluster and a red cluster. What do you think of the clustering? Looks good? Nice clusters? Yeah, I don't like them either. Let's compute the centroids, shall we? First, do you think that they will be close together or far apart? The blue centroid and the red centroid. Close together? Sure, because there's quite a lot of points and they were assigned at random. There's no particular reason why all the reds have to be in one place with a very different center of gravity from all the blue ones. Fine. Okay, do you think it's going to be slap bang in the middle here or somewhere else? Maybe pulled a little bit towards where there's more points, so a little bit down and left, yeah? There? Something like that. You'll get closer, don't worry, as you see more of this. Okay, what's next? We will forget the old cluster IDs. Boom, forgotten. And then we are going to do something of such astounding brilliance you will never see it coming. We're simply going to give each point the color of the centroid closest to it. So, red or blue for this one? Red or blue for this one? Blue. How about this one? That is why we let the machine do it. It is better at this than you are. Turns out that's red. How do you feel about the clustering now? We getting somewhere? Yeah, looking better. Let's keep going. Let's recompute the centroids and take a moment to guess where they're going to be. They're going to be far apart or close together? Far apart, and how are you doing? Yeah? Okay, you kind of get what these things are now. And again, we forget the labels. And again, we do the same thing. ID of the nearest centroid. And then we go round and round doing the same thing until the clusters stop changing. Spoiler alert, there will be no further changes. This is the last solution. So round and round, nothing changes. These are our clusters. Job done. So that is k-means. Now, standard burning questions from the audience. I want to see if I can anticipate them. 2 questions that are burning. How do you pick K? That's not on my next slide, so I'll address that right off the bat. Depends if we're doing analytics or if we're doing machine learning. So again, you can use the same algorithm for different applications. If you're doing analytics, you don't know what you're hunting for, you're just trying to get inspired. So what might you do? In a loop, K equals 2. Anything interesting yet? No, how about K equals 3? Anything interesting? How about K equals 4? And you look at the results every time and you see if anything feels compelling to you. It's a pretty nice approach to data mining. If this is a machine learning application, you know exactly why you are trying to do this. Maybe you have some kind of nice app where the users put pictures of themselves and their friends, and then based on the photographs for everyone's amusement, in some way it splits that into 2 groups, puts party hats of different colors on the 2 groups and says these are your sports teams for beer pong or something. Then you know what the purpose of that app is, and you've just said it's 2 teams that you're trying to make, so then fit for purpose, 2 will be the split. It depends what you're using it for. Other questions? Some typical ones I tend to have yelled at me. Google engineers are like, will it stop? Tell me, will it stop? Will it just keep going round and round? Because you know what? If I get a point that's equidistant between these 2 clusters, it could just like bounce back and forth between the 2 because the coin keeps flipping. Whew, take a deep breath. Yes, it converges because the actual implementation is a little smarter than this and involves, of course, a loss function. And the loss function has to do with the distance of the points to the nearest centroid. And so, even if the point is equidistant, well, the distance computed is still the same, so the scoring for the loss function is still the same. So even if the point flip-flops from blue to red, it still considers itself to be finished and will stop and give you the answer. How about same result every time? What do you think?
Yeah, I think so.
Oh, fight! Fight! The answer is no. The way that you do the random sprinkling of the labels does matter. Imagine if you have 50 data points and you ask for 49 clusters. Try that out. You will notice that you don't get the same result for which one has 2 points in it every time. So I have a try it first slide for all our methods, and here you will try it first if you have no labels. This tends to be the first unsupervised learning thing you go for if you have no particular reason to suspect you should be using a different one. And this is where you want to split your instances into groups. Another kind of unsupervised learning approach is one where you are looking for anomalies, what is unusual. That's a different thing, we won't talk about it here. This one is where you're going for separating things into groups. Now, strangely, I can never understand this. Students get K and N confused with K-means. And I don't know why they do this, because these techniques have nothing in common. Except that maybe if you just squint just right, these 2 N's together look like an M. That is about it. That is all these techniques have in common. So let's see what K nearest neighbors is. It is part of a class of algorithms called lazy learning. Oh, so cute. And what is lazier than having your recipe be the whole data set? I'm not going to bother to summarize it for you, just use the whole thing. So let me show you an example. Here is a desk area. We've got engineers and managers sitting in this desk area. We have the north-south coordinates and the east-west coordinates. And we'll see this thing in action with K equals 5. So now the technique reads 5 nearest neighbors. You have no idea what's coming. That K, by the way, it is a hyperparameter. And so we'll need to tune it, and we'll see that shortly. But for now, meet Heather and Sophie, that's where they sit, and we will use 5 nearest neighbors to diagnose them as engineer or manager. First, Sophie, we will find her 5 nearest neighbors in space. There they are. And all we do is we say, what's the most common label? let's give her that label, so we say she is an engineer. Then we do the same thing for Heather, and that manager is just closer than this engineer, and so Heather gets the manager label. Now, of course, K matters a hang of a lot, which is why you will want to do hyperparameter tuning, and the way you can tune it is simply the start at 1, go to 2, go to 3, if you wish to. Hyperparameter tuning is easy for this case. It gets hard when you've got lots of different hyperparameters that you have to deal with, and it takes a long time to rerun your model, and now you can't just brute force find the right answer. Now, let's look at the effect of K. If we set K to 15, there is nowhere that poor Heather can hide. She will get the engineer label just simply because there's more engineers. If we set K equals 1, and we have my desk nearby, and I'm a decision scientist, then, or statistician, whatever I am, then poor Heather gets that same title, decision, whatnot, even though there's only one of me. And so K equals 1 is where you get judged by your one weirdo best friend rather than the diversity of the friendships that you hold. So you will want to tune and see what's actually working for you. So this has nothing to do with K-means. This is a supervised learning technique. All the following techniques will be supervised learning. It was only K-means that was unsupervised in this list. So when do we try it first? If we've got labels. They can be any labels. They don't have to be categories. They can also be numbers. We can find my 5 nearest neighbors and use them to predict salary by finding the median salary among those nearest neighbors, right? Same kind of reasoning. And of course, we don't only have to do geographical stuff with it. We can say, who are my nearest neighbors in the audience in terms of shoulder width, maybe, and torso length, and we can use that for sizing a t-shirt. Use that to predict t-shirt size. And it doesn't just have to be 2 features, we can do this for more features, but careful. This really requires a tall, skinny data set. It doesn't like situations where you've got too many features and not enough instances. It really suffers from what is called the curse of dimensionality. So what is that thing? Such a machine learning term, it's great. I like to think of it as some methods really don't like it when data points are lonely in space. So let me explain. If I shine a bright light from that wall onto there, and it projects all your shadows against that wall, so now your shadows are in one dimension. You are all on top of one another and not lonely at all. Add another dimension along here, and now you're a little more spread out. Now I'm going to add another dimension. Which floor of this building are you sitting on? It's still same east-west, but now the height varies. All of a sudden you look around you, where are my friends? It's lonelier. Now I add another dimension. Which hour of the day are you doing your vigil? Now it's really lonely. And so every time I add a dimension, I don't require only the same amount of data to compensate for it. I need exponentially more people for you to have as many friends around you as you do now. And some methods are really sensitive to loneliness, and so they are really sensitive to the addition of one more dimension. Things look very empty around the data point. That is what the curse of dimensionality is about. Okay, this is great for fast model updates. What can be faster than finding out what Heather is and just putting that row underneath the rest of the data set? There you go, there's your updated model. This is good when local structure is key. When you think that maybe if there's a few statisticians around, other ones just pop up like mushrooms, rather than more statisticians as we head towards the North Pole. If you're dealing kind of with the first one, this is a good bet. And in order to pull it off, you have to be able to actually store and query the whole data set, so that shouldn't take forever. Next, support vector machines. That sounds crazy cool and difficult, and you'll be so disappointed to know that all it is about building walls in your data. Now for this section, I'm going to do a fun kind of thing. We're going to develop the method step by step, so we'll go through actually multiple methods in this class of things, We made 4 of them. Each time we get an upgrade. And it's sort of a historical note also. How were they upgraded through history? And the rules for this section are that we are only allowed to use one straight thing to separate our data. So maybe it's a line, maybe it's a plane, maybe it's a hyperplane. If we want to do curvy stuff, we have to go to a different method. That's allowed, it's just not in this section. So, our application. We have a map, and we have only some of the buildings on that map highlighted here. The blue ones are shiny modern skyscrapers, the pink ones are gorgeous old historical buildings. And you are a city planner. Your job is to make a neighborhood boundary. Where is the historical neighborhood? Where is the modern neighborhood? And what shall we do to separate them? How about put a line? Not that line, not that one. How about that one? Okay, you'll accept this one, will you? What we've just done is tried on various lines that fit, and then we got the first one that works, and we accept that. That method has a name. Stop when you get one that perfectly separates them, and its name is Perceptron. For that, you get this name? Seriously? I'm machine learning people. Now, you could have picked that solution. You could have picked this solution. You could pick that solution. There's lots of options. There's lots of options. How do you choose? Maybe you have a preference. Maybe you want to have a principled selection between these. Well, I submit to you PowerPoint skills. Why that thickness of line and not that thickness of line? Or maybe if we stick to the city planner example, you know that one day your successor is going to put some kind of path where you have drawn the boundary. And you don't know if they're going to put a bicycle path or a highway or what. But you notice that for some thicknesses of roads here, it smashes buildings. And you still have a heart. And you think maybe you don't want to smash buildings unnecessarily. And so you say to yourself, some of these options are unacceptable, I'm not going to consider them. And looking at this, you're like, actually there's a way I can squeeze a slightly larger road in here. There it is the biggest one I can put. And the line in the middle of that, that's the one I'm going to go for. And that is named, very creatively, I'm guessing it's statisticians, Maximal Margin Classifier, because that is exactly what it does. It attempts to have the maximum margin around the boundary. And so that's our next method upgrade. What are support vectors? I would have called them points that matter. See, if I take this point and I smash it, it doesn't change my solution in the least. This one, I can move it off the map. As long as I don't move it too close to the road, it doesn't matter to my solution. But these ones over here, if I move them, I get a different road. Those are my support vectors, and this method is going to think about putting boundaries, taking them into account. Now, R, this is a plot in R, is known for its beautiful plotting, and this is not it. I don't know what part of the 80s coughed this up. Like, what colors are these? What's cyan and magenta, and why is this straight line pixelated in this decade? The point, though, is that R is really good for prototyping, and this is what you can get with about 2 lines of code. And with a few more, you can get the beautiful plot. But 2 lines of code, and you fit and plot a basic support vector solution. It's pretty nifty. It doesn't take a lot of effort. Whereas if you tried to do it in some more serious production-worthy thing, then it would take you far, far longer than these 2 quick lines. So you try it out in this kind of environment, or some Python package if you prefer that, and then you only go to the more serious thing when you're like, okay, this kind of approach is working for me. What if your historical buildings have no respect for anything? Look at them there. They're in the middle of our modern neighborhood. How dare they? We statisticians have a very creative name for this situation. Wait for it. Not linearly separable. As in, you cannot use a line to separate the red from the blue. And the previous 2 methods require you to have linear separability, so they cannot work. So we must upgrade. And our upgrade is to the support vector classifier. The support vector classifier is the kind of solution that most city planners would roll around to eventually. Okay, we'll let them violate the line, but we'll tax them for it. And so now we simply add a tax to the loss function. Things can go on the wrong side, but they do get penalized. And how much you tax them is a hyperparameter that's up to you that you're going to have to tune. So here we go in R. We can see that we have not got perfect accuracy there, but I much prefer this solution to a horribly overfitted one that tried to do some contorting around these two so that it did have perfect performance. I would look at that and be like, is that really going to work on the other buildings that we've left off the map? This is a pretty sensible and reasonable boundary. So that's our support vector classifier. The worst possible situation is where the modern buildings grow up around the historical buildings. This is terrible. Because for this whole section, we are only allowed to use one straight thing to separate the red from the blue. Where are we going to put it? Okay, let's try out our previous support vector classifier. And it suggests, because we have more modern buildings than historical buildings, why don't we put the line up there in the top right-hand corner at plus infinity, plus infinity. Call everything modern and be done with it. That's a little better than calling everything historical and be done with it. Can we do better? We want one more upgrade to support vector machines. And what we will rely on is called the kernel trick. And to explain the kernel trick to you, I have a prop. My trusty cloud, it's a cloud towel. Oh yeah. My towel of the kernel trick. Now, I need you to use imagination. Do your best. And imagine this same thing on my towel. Red ones in the center, blue ones around them. And you need to use a straight thing, a line, a plane, a hyperplane, whatever, to separate the red from the blue. And you look at this and you look at this and you get angrier and angrier and greener until eventually you have become the Incredible Hulk. And the only solution you can think of is to punch the thing because it angers you. And what you do is you punch the space, adding an extra dimension, and converting your other axes. And now I can use a plane to decapitate this thing, because the red is now above the blue. So that is what the kernel trick is. And let me show you another plot of that. So here I had some data points. I then make a punch and project them into more dimensions. And in this new space, I can use a plane to cut. So I'm still using a straight thing and I'm still using support vectors. It's all the same business from the previous step. It's just I have transformed the underlying space first. And then once I've done the cutting, I can project down my solution back to the original coordinates. It looks like I used a circle. I really didn't. I used a straight thing. I just punched the towel first. So when frustrated, punch the towel. And at this point, my Google engineers are like, this is the most technical thing you have talked about all day. Tell me more about kernels. Give me all the equations. I have to be like, no. Read a textbook. That's not in the scope of this thing. But then I think, okay, I can't just leave them hanging. I should maybe point them to an educational resource. And I thought to myself, the internet is a magical place, a marvelous place. This is called the kernel trick, yes? I really wonder, is there a website called oneweirdkerneltrick.com? And it turns out that there is such a website. And it is in fact run by someone with a sense of humor who has put real learning resources on there. That, for example, is Vladimir Vapnik, who's one of the co-authors of the original Sport Vector Machines paper, and the other co-author is our head of research in New York, Corinna Cortez, and her face is also on there, along with a lot of other stuff you can go read if you're interested. So oneweirdkerneltrick.com. And when we do an SVM plot in R, we can see that we have much better training performance, only one mistake. So that's our final method. We're like the Incredible Hulk. We punch the space because we get so frustrated. We add a dimension. We transform the original dimensions also as part of doing that. And then we chop it still with a straight thing, project it back down, call it done. So when are you going to try this thing? If you've got binary labels, if you want a flexible boundary shape, not just linear, and this is a solution that lends itself best to moderate scale. If you're working with really large scale, there's another method we'll look at later, logistic regression, where at Google we have done more engineering effort to make that one scale friendly than this one. So you'll prefer logistic regression at larger scale. And now we'll have trees, tree-based methods, decision trees, random forests. Let's have a look at what's going on here. These are, in a nutshell, a bunch of if this, then that for your data. And so I thought, why don't I manufacture an if this, then that rule, the traditional programming way, about my movie preferences, so you can all recommend movies to me. So I thought about what I like, and I came up with this rule. If it is a mystery, a thriller, or a sci-fi movie, hand it to me, I'll like it. And then I thought, but am I not a data scientist? Come now. Should I not maybe add data and see what the performance is of this rule, this algorithm or recipe that I have? Because it doesn't matter whether it came from a machine learning system or I dreamed it out of thin air, I can still assess the performance the same way. See what it predicts, see what the truth is, and look at the results. So what I did was I grabbed the IMDb database, I shuffled it, and then until I couldn't be bothered anymore, and my attention span is about 200 or so, I rated like it, don't like it, like it, don't like it, like it, don't like it, I gotta watch that one, like it, don't like it, anyway. And I have for you the results from the training set, which is something like 100 movies. Let's find out how this rule does. Turns out, precision's pretty good, and I'm aiming for precision here, you know, like with the books. I'm pretty busy, I'll never be able to watch all the movies I like, so let's have a don't waste my time kind of approach here. I can leave out some good ones, but you know, if you suggest it, hopefully it's likable. And if you follow that rule, 3 out of 4 are going to go down nicely. It's a relief to me to see that recall is low. That suggests that maybe this doesn't cover the full diversity of my movie preferences. If this were 100% recall, it means I have a very one-track preference, just that, nothing else. Then I thought, all right, why don't I let machine learning have a go? And I'm going to ask for a really simple model based on any of the features in IMDb, but a decision tree with just one node. I'm going to show you the rule on the next slide. I want you to look at it in this order. First, watch the precision go up. Then watch the recall go up. Then read what the rule is while I stand here cringing. Here we go. If it's long, I'll like it. Above 127 minutes, yes, otherwise no. Now, what does this mean? Well, from a data science standpoint, the only thing it means is that in these data, this rule outperforms my other rule. There is no other thing that it means. If I'm tempted to start spinning stories all about how, yeah, maybe this means something about directors investing more effort in longer movies and so the quality of the movie is whatever, or some story about how Cassie is so pretentious that if I'm tempted to start making such stories, I need to be aware that I'm in danger of overfitting, and I shouldn't take myself seriously unless I go and carefully articulate that story as a hypothesis and then test it in another data set that I didn't use to form this impression. And if it holds there, then it holds. Now, I didn't have to have such a simple rule. I could have gone for a slightly more complicated one. So let's have 2 nodes. Ah, dear. I'll like it if it's long, but if it isn't, let's have a thriller. Slightly lower precision, but unfortunately this now covers 2/3 of my movie preferences in that set. So simple creature, simple creature. But I could have an even longer rule. A lot of decision tree algorithms, if you don't tell them to stop, they will just keep going and going, and they'll make you quite the tree. Let's read this one. It says, is the runtime more than 132.5 minutes? If yes, then is the runtime more than 143.5 minutes? If yes, is the runtime less than 165.5 minutes? If yes, is the runtime less than 156.5 minutes? Then she'll like it. And your spidey senses are tingling, I hope. What word is bubbling to the tops of your consciousness? Overfitting. Yeah, it fits these data really nicely, but it is probably utter nonsense for the rest of reality. This rule is not going to work if I try to predict movie preferences outside this data set, even though it works really well in training. Look at that, 84% precision, 88% recall. Now, because they tend to be implemented so they make you these big convoluted rules, you will need to run a pruning algorithm to snip, snip, snip back their enthusiasm. And you'll say something like, no more than this many nodes. How do you pick how many nodes? Well, it is a hyperparameter that you're going to need to tune. So that's why you do that tuning step. Decision trees are if this, then that rules, and the resulting recipes are easy to describe to humans. Notice how I don't say interpret. I'm saying easy to describe. I mean, it's hard to beat if someone asks you, how does this thing make its decisions? I say, well, it's as simple as, is it above 127 minutes or below? Very easy to describe. But please don't interpret them without going and following up in other data and actually checking your interpretation. And a little note about interpretability. This is a hot topic for machine learning and AI. Should models be interpretable? And then there's all this fighting. And it's such an angsty debate. And I watch this and I just feel like, can I please translate for both sides why you're miscommunicating? All the ones who are anti-interpretation are doing the machine learning side of data science. Make it work. And they're saying, come on, you don't need to know how it works. Your whole goal here is make it work. So why would you give up performance to be able to ogle that model? That has no use to you anyway. And the other side is like, but how will we get inspired if we don't look in the model and if we can't read it and interpret it? Well, that side is not doing the same work. They are doing data mining, descriptive analytics. They want to have an opportunity to get inspired by data. It's an entirely different process that they're after. And so both of them are right. They're just doing 2 different jobs. If your job is performance, don't force yourself to only go for these easy-to-read recipes. Get performance and test it properly. If your job is to be inspired by data, then of course you need to be able to see what it's saying to you. And so if your job is data mining, descriptive analytics, this is a lovely, lovely tool. I like to do this when I want to get inspired by data. Even if this has nothing to do with what my final model is going to look like, it's still nice to see how it wants to split the space and suggest to me which parts are worth playing with. Now, behind the scenes, what's going on? So here I have linearly separable yellow and green. Here I have non-linearly separable yellow and green. Here I have the tree. Here I have the support vector machine. And what we see is what we expect over there. Linearly separable can be done with a line. Here it can't. What is a tree doing? A tree starts with one of the features, x1, and says, where shall I put my vertical line? And the way it makes that decision, there's all these equations that you can look at that sound awfully intimidating. Don't worry about them. Think of it in terms of mixing cocktails, let's say, concentrations of stuff. It is trying to get, most of those metrics have some notion of the purity of the result. So look at this glass. No matter how fat I make this glass, I still have the same concentration of yellow and green. Until I hit this point, and then I have a little bit more green, so my yellow concentration has gone down. So that's not an ideal place to put the line. If I wanted a purer mix of yellow, this would be the best place. And over there I have the purest mix of green. Once I've done that split, I go, all right, down this branch, anything to do? No, it's all green, so I'm finished. It stops short. How about over here? Anything to do? Well, where can I split this one so I get the purest concentration of green on one side and yellow on the other side? Yeah, that one looks good. Anything else to do? Nope, then I stop. And that's kind of how they work. And when you have this sort of space, it's like trying to tile your poor bathroom when there's a diagonal bit. Smaller, 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 smaller tiles, too many branches. If you actually plotted this in your training data, you might be inspired to do a little rotation of the axes, and then it's hole in one. So then you can actually solve this with a decision tree because you do a bit of feature engineering. You have a lot of situations where lovers of some or other method will say, hey, you don't need that other fancy method. Look, we can do the same thing with our method. They just tamper a little bit with the features first to make the features friendly to their method, and then their method works. So you can do a lot by altering the features, or you can approach it by altering the algorithm. So when do you try this first? When you've got no labels, when you want an easy-to-read model, or when, if this, then that seems like a promising structure for your problem. What is bagging? That stands for boosted aggregation, and that is not as intimidating as it sounds. It also isn't only for trees. Let's look at it for trees. The length of my dataset is the number of instances, the width is the features. What bagging does is, instead of trying to swallow the entire dataset in one go, it at random takes some instances. It makes a tree with those, it stores the tree. Then it puts back those instances, and it at random takes some other ones. So it is sampling with replacement and fitting a tree every time, remembering all the trees, and then at the end, it lets all the trees vote to give you an answer. So this one says she'll like it, this one says she'll like it, this one says she won't. Now, this has some fairly nice properties. Under certain circumstances, it actually has better performance than not doing it. But even if it didn't have a better performance, a very compelling reason for this is that you might not want to swallow your data all at once. You can parallelize all that and handle little bits of your data all separately, fit all those trees separately, and maybe that's just a lot faster. And since the performance may even be better, that's some of the black magic behind this boosted aggregation stuff, it's worth trying. Now, what is random forests? Now, that sounds like some science fiction thing, like something from Lord of the Rings or The Hobbit, like the forest rises up and marches around. Random forests is actually kind of like bagging, but on the width, not the length. And usually it's implemented with both of them. So you take some sample of the instances, and then within them you take some sample of the features, so you end up with kind of like a little square of your data, and then you fit the tree on that little one, and then you do this again and again and again. This is a really great technique for data mining, because if you run your data set through this, if all of your features are equally useless, because you're doing this random sampling, you should expect that you will see your features crop up in the trees with about the same frequency. So if you just count how many times the feature was selected by your tree, and some of them are more popular than others, then that might tip you off to pursuing that feature. So you're inspired to do something with that. Now, if we're going to allow things to vote together, why stop at just trees? Why not allow a neural network to vote next to a tree, to vote next to a perceptron, to vote next to Cassie's opinion, to vote next to your opinion all together and have all these opinions vote. I can change the weights on how much each vote counts. Of course, Cassie's vote gets 95% of the weight and so forth. That is called an ensemble. What ensembles are really great at is covering one another's faults, if you will. So think about it like this. If you wanted to do your decision making by one awesome, benevolent tyrant who is really, really good and on the whole, better than everyone else in your organization at decision making, that would be fine unless there's an Achilles heel, a fatal flaw. On the whole, really good, but there's a blind spot, and if that blind spot is hit, that is critical failure. Well then, maybe you want to have a backup decision maker who is not that much worse at all the other parts, but covers this critical failure. Pretty good at that part and has a different flaw. Well, then we can have them balance one another out, and hopefully, where they are both decent, there's not that much of a performance degradation, so on the whole, this feels like a better system. The flip side, though, is when you start composing all these various methods together, the engineering and maintenance and upkeep and reliability issues become a nightmare. So a famous example is the Netflix prize. It was $1 million prize that Netflix gave for making a cool recommendation algorithm. And the solution there was a crazy big ensemble model. And of course, Netflix nobly paid up because that did win the competition, gave the best performance. Or they didn't implement that thing because that was not going to work sanely in production, just too much going on. All right, what is naive Bayes? What are Bayesian methods in general? They summarize to this: when in doubt, use Bayes' rule. Now, what on earth is Bayes' rule? It is a piece of math which, if you're not careful, you may fall in love with, and then it finds its way into all kinds of places in your life. Maybe you've tattooed it on yourself, or maybe you're making art, light fixtures, like this is an actual light fixture, in the form of Bayes' rule. And so, not in the spirit of equationsing, but in the spirit of art appreciation, let's make sure we know how to pronounce this formula. Now, there's nothing controversial about this formula. If you've heard of classical statistics versus Bayesian statistics as a controversial thing, that's for the statistical testing. That's very philosophically heavy. For machine learning, though, there's no philosophy here. This is borrow whatever math you can find lying wherever, and if it works, and doesn't matter. And actually, if all we're using is this formula, there's no controversy at all. This is a mathematical formula with a proof it works. So how do we read it? Well, whenever there's P with brackets, that's pronounced probability of. And A and B here are just events. Events like the coin comes up heads or falls on the floor or whatever. Events like your roommate forgot to wash the dishes, events. And this vertical bar that you see over here and here is pronounced conditional on, or given that, or in a world where. So let's practice conditional probabilities real quick. We'll pronounce things like the probability that we have a cat given this evidence is equal to blah, blah, blah. So what does this boil down to computationally? It's all about counting things. In fact, we're going through this quick little demo just to show you the simplicity of the operations involved. Super simple. Look at this. Probability of cat. How do we get that? How many pictures? 8. How many of them are cats? 4. 50%. How about probability of lots of green pixels in a world where cat? Well, very simple. We said in a world where cat, so why are we bothering with all the other ones? We only care about the cat ones. And then the formula is simple again. It's the straightforward thing. How many total? 4. How many have lots of green? 2. And there's our answer. Very easy to make these manipulations. So what are we doing? Dividing, ignoring, and counting. Those are very easy for a computer to do as well, and that's going to be the point. Now, naive Bayes tends to be baby's first spam classifier. That's the favorite example in machine learning courses, when you make the first spam classifier. And it's naive in the sense that it says my features have nothing to do with any of my other features. The presence of the word free has nothing to do with the presence of the word shipping. Now that's a little naive. We know that there might be some relationship between those words, and we know that if we were trying to model the universe carefully, if that were our goal, this would probably be a bad fit. However, we're trying to get the thing to work, and it might just work even if it's naive. So maybe we'll just try it anyway and see how it performs, where it's making these clearly ludicrous assumptions fine. So what's great about this thing is that it is going to use these elementary operations. And the way that these are all composed in a formula, I have a little link down there for you in the slides. Really, an undergraduate on their first day of a probability course learns all the components that you can do to put this formula together. So if an undergraduate student can do that on the first day with no background at all, it's not anything too deep. It's just composing what we had before and using some simple, straightforward manipulations, which you can find in the link. Same principle though. Counting, multiplying, dividing, ignoring. That's it, nothing else. And finally, when it's done, you interpret the results as, given all this evidence that you've put in, that treats all the evidence as completely independent from all the bits of evidence completely independent from one another. What's the probability that I have a cat versus a not cat? And then you can either output the label that is most likely, or you can jump for joy that you're dealing with probability outputs, because now instead of just simply getting the flat label, you can say, hey thing, how sure are you? If you're saying some number that's too close to 50, maybe you don't know what you're talking about, and maybe I prefer not to listen to you, maybe I prefer to send this to some other process, maybe have a human look at it and make the judgment call. Whereas if the number is very close to 100% or 0, then I can go with what the system is saying. So, naive Bayes, when are you going to try it first? If you have category labels, and if you have category features, like text, for example. Now, having category features is no sweat. It's very easy to turn your continuous features into categorical ones. You have measured all kinds of things about my torso, length and width and whatever. Well, you can turn that into small, medium, large with no problem. Going from the category in the opposite direction, that's the hard one. So you can always turn your features into categories. When there are many features, this is a great idea. This handles a lot of features. And with text, the way that data actually tends to be encoded is you have all the possible words that one could meet in an email, and you are asking present or absent, or how many times present, how many times absent. So you have a bunch of zeros. We saw in this email no times the word hippopotamus, and no times the word tiger, and one time free and one time shipping. And so we have in that row counts of that sort. There's lots of features. This can handle that situation. And it's also great when you need your code to be simple. The operations are super simple. Now there's a naive version, this counts thing. There's also a less naive Bayes. And that one involves crazy cool things like likelihood function, priors. Warning here, this is harder, but it is so cool. And if you're not careful, you will really fall in love with things. And then, like me, you might sink several years of your life into this. So watch out, maybe don't flirt with it too much if you don't want to fall for it. What's next? Regression. We've already seen regression. It's putting lines through stuff. It's about finding lines that are as close as possible to your data, like our smoothies example. And In statistics, regression refers to fitting models of this form. What is this saying to us if we imagine a spreadsheet? All the features of the columns of the spreadsheet. So what are we doing? We're finding something to multiply the column by. Every column gets its own thing to be multiplied by. And then once we've done those multiplications, we add it up, and that's the prediction. So that kind of form. And this has been around for a really, really long time. Why did it take 200 years for us to roll around to this machine learning business if this has been known for a long time? Well, the way you use the algorithm is different. What they were going for is fitting the algorithm and describing their universe, and there were notions of statistical testing around that algorithm. What we are doing is taking that piece of math, after we have split our data, trying it out to see if it makes a recipe that looks worthwhile when we apply that recipe to a second dataset. This entire machine learning thing is the result of enough data so that we can afford to split it into multiple pieces and then apply a lot of different stuff to the first piece, check if it works in the next piece, and then have a final safety check in the last piece. Machine learning is an attitude that is around splitting data, and when Gauss was starting out with this, there wasn't a lot of data to go around. When are you going to try this linear regression approach? If the output is a number, a dosage, a dollar amount, something like that, a calorie count, and if the value of the feature is more meaningful than just a threshold. And to explain this, let me tell you another little story about developing this course. In the early days, I didn't have these slides, the try it if slides. And I remember presenting this in Zurich, and we have some lovely Googlers in Zurich who are really kind and want to make sure that my flight home is as entertaining as possible. So I got some emails from them that went as follows. Hey Cassie, we see you like long movies. So have you heard of this 6-hour movie? And have you heard of this 5-hour long movie? Very kind, but it's a fundamental misunderstanding of what the decision tree model before was saying. That model doesn't say the longer the movie, the more I'm going to like it. That model says, if the movie is above 127 minutes, recommend it. Otherwise, don't. There's nothing about the value of the feature being more meaningful than the threshold. So if they'd really understood that message, I should have gotten some people recommending me movies that were 128 minutes also. Or, 2.5 hours, not straight to the 5 hours. That kind of reasoning of every additional minute adds an additional bit of goodness, that is reasoning that is consistent with this sort of model. This kind of model is the one that says longer is better. For every additional gram of carbohydrates we add to the mix, we get more calories. It's not just like there's a threshold. If we're above 40 grams of carbohydrates, it's infinity calories already, and we should all panic. So this one, it has the structure of adding a little more gives you a higher prediction. Now, the simple linear regression thing does not transform any data for you. It just takes those columns, finds something to multiply them by, and off we go. But there are other flavors of regression, more interesting, complicated ones. Here are some popular ones you may run into. Kernel regression, you already have a sense of what that might involve now that you know what kernels are. The one we'll look at is logistic regression. Logistic regression is one of the most popular approaches to binary classification. And we really love that here at Google because it is very nicely scalable. So binary classification here, at enormous scale, we like this kind of approach, and we like neural networks also. So let's have a look. We're going to apply this to an utterly made-up example involving, can knowing the hours that a student has studied help us guess whether they are going to pass or fail an exam? Let's see our data. On the x-axis, we have the number of hours they've studied from 0 to 40. In blue, the ones are passes, the reds are fails. And as you're looking at this, you're like, of course hours of study has nothing to do with passing and failing. Of course. Or are you looking at this and thinking, yeah, there's something to it? I'm seeing that it does look like there's a little more failing on the low end of the study spectrum and a little more passing on the high end. So let's see if we can make a model. We're supposed to be in a putting lines through stuff section, aren't we? So let's put a line through it. Now, we would love to interpret this as a probability. We've seen already in that previous section that it's nice to get probabilities as output. But let's read. If I study for 2 hours, I have what? A negative probability of passing? That doesn't even make any sense. Probabilities can't be negative or more than 100%. So if I insist on getting a result between 0 and 100, I'd better try something else. So here's what we're going to do. Logistic regression. And I'm not going to show you what's happening there behind the scenes, details. I'm going to show you essentially how you should think about this, and especially at scale. What you're going to do is you're going to do something like a predicted probability in the sample probability of passing at each hour. And then you're going to do a little bit of converting those individual things to a different scale entirely. So you push them through a different function, and I've actually grayed out that function. It's the logit function. You don't have to even worry about what that function is. The point is simply this. When you have done that transformation, does it look like a shape that we are familiar with? It looks an awful lot like a line now, doesn't it? And so now in this converted space, our studied versus this logit, whatever on earth it is, we can fit a line model to it. Great. So we can use this model to predict this logit thing. Was that what we asked for? No, we didn't want a logit. So let's undo the damage. Let's take this model and convert it back to our original coordinate space. So it's like flip it, fit, and reverse it. And when we pass this thing, this line, through another function, ta-da! That looks a little more through it, right? This lovely S-shaped curve. These S-shaped curves, they are called... What is a psychoanalyst's favorite mathematical function? Sigmoid Freud. It's too late in the day for this, isn't it? So these are called sigmoid or logistic functions. And when you see these things in the context of data science pursuits, typically that sigmoid serves the function of forcing your output to live between where you have said it must live. Probabilities have to stay between 0 and 1. Okay, this is a way to force it to stay there. But another lovely thing that you get from the sigmoid curve is something that you might remember if you have ever taken an economics class. I have an undergraduate degree in economics, so I still remember the nightmare. So who's taken an economics class? Anyone? I see a few hands. So do you remember really early on there was a law of something? Diminishing marginal returns. Exactly. This is a way of algorithmically, mathematically putting diminishing returns into your model. So let's read what it says here. If I study for 20 hours, pass-fail for me is touch and go, right close to 50%. But let's say that I study an extra 10 hours over that. Look, my probability is pretty close to 100% of passing. I'm pretty sure I'm going to pass. So if I put another 10 hours in over that, am I going to be again that much more likely to pass? No, I'm already passing. Or, if you want to put it a different way, at 20 hours, it's touch and go. If I reduce by 10 hours, I'm failing, so I may as well not study. Standard undergraduate logic. So diminishing returns is encoded nicely in this model. So you get to peg your output where you want it, you get diminishing returns from your sigmoid functions. And this is more like a model of probabilities. And again, to classify new instances, either we can simply assign whichever label is more likely. So if it outputs for me 0.55, then I will call it a pass. Or I can say 0.55 means you don't know what you're talking about model. Let's call that the I'm not sure zone and actually ask a human for their opinion. So logistic regression is a great tool for binary classification, and it works well at scale 2, including at Google scale. We use logistic regression a lot around here. Now, it can also work not only for binary labels. There's a version that works for multi-class classification, and that is multinomial logistic regression. So it's not only pass, fail, or cat, not cat. You can also use it for cat, dog, bear, elephant, giraffe. So this one, the binary one, works for binary labels. You can also do multi-class. And it's a good choice when you have that sense that diminishing marginal returns is part of what you're dealing with. And it gives you probabilities out, which is very nice. And probabilities are pretty useful for ranking stuff. Like if you want to serve the user the song that they are most likely to listen to next. So for each song, you predict the probability that they're going to interact with it. And then you can order it by the probability results. That's one simple way to do some ranking. The last section is neural networks or deep learning. I make it sound like there's a choose-your-own-adventure element, one or the other. They are actually pretty much synonyms. Deep learning refers to neural networks with more than one layer, or deep neural networks, and deep neural networks were named when there wasn't much computing power to go around, and so we could barely dream of having maybe 2 layers. We stick with 1, but like maybe one day we can achieve 2. We shouldn't even hope about 3. Today, they've all got many. They've all got more than 2, the real ones, the production ones. They might have thousands. So they're all deep. All neural network stuff is deep learning. Feel free to use this as synonyms. All right, so we're going to dive into this. And a small disclaimer. We shouldn't even hope about 3. Today, they've all got many. They've all got more than 2, the real ones, the production ones. They might have thousands. So they're all deep. All neural network stuff is deep learning. Feel free to use this as synonyms. All right, so we're going to dive into this. And a small disclaimer. At the end of our less than half an hour section on this topic, your understanding of them will not have improved at all. Hopefully, if I do my job though, you will understand why that is and you'll be okay with it. Now, feedback I hear from many semester-long courses on neural networks, pretty much the same. The student spends an entire semester and also doesn't understand them any better. So for the low price of less than 30 minutes, you will get the same improvement in understanding as you might get from an entire semester. So shall we dive in? What are neural networks? Not that. That. Layers upon layers of mathematical transformations. Not anything magical. Just a lot of operations stacked together. And let's see an example, and I don't want you to take this example too seriously. This is just an analogy that's going to get our thinking started. So let's have a look. In case you didn't realize that it's a really bad idea to let me into the kitchen, we are back with a cooking analogy. So we're going to have some features, and they will be of plant, animal, or artificial origin. And they're going to vary for each individual instance. So think of this as the column headings in your spreadsheet. So your spreadsheet is sort of turned this ways in my example. And our first instance has, for its plant, some broccoli. You know how much I like those sardines, so that's our animal ingredient. And for artificial, we have mint-flavored candy canes, because I submit to you that there is nothing natural in these things. And then what do we have? We have an output layer that is going to output something like tasty or not tasty as our label coming out. And inside we have some hidden layers which are thus named because they are hidden for your own good. Because if you look into the hidden layers, the abyss stares into you. So, good advice to leave them hidden, but we're not going to take that advice today. We're actually going to look inside them and see some of the units in these hidden layers, also known, if you prefer the more futuristic sounding jargon, as neurons. And the role of the neuron will be played by a blender. So, what are we going to do? We're going to take our individual ingredients here, but we're not going to take the whole ingredient all in one go. This can of sardines is much too precious. We're instead going to take some weight, some amount of each ingredient, and we will put them all into our blender, and we will blend them together. And I know what you're thinking at this point. You are dying to taste it. Indeed. And think of the taste test as the point where you're going to decide whether to allow this unholy mix to move forward or to not use what's there at all. This taste test is kind of like the activation function in neural networks. We take the thing that we've blended up and we do some kind of transformation to it, in this case using our taste buds and asking ourselves, is it good enough to move forward or not? So think of that little taste test as a little twist on the plot, adding a little bit of non-linearity, and I'll tell you why we do that shortly. But as a taste test, we taste it, apparently it's yummy, and it gets to move forward in its entirety. Now I'm tired of writing the word weight, so I'm going to indicate the weight with the thickness of the line. So far, so good. Everyone has blended stuff, yeah? In different weights of ingredients, yeah? Good. Next, we have another unit, or blender. And we're going to take other weights of these same ingredients, blend them up, taste it, that doesn't go forward, and then we'll have another blender. We taste that, it's delicious, and there's more in the next row. We blend up these various mixes in various amounts. We taste all of them. Some of these go forward. We blend those up in various amounts. We taste that, and there's our result. Whew. Now, all of you have been in the presence of a blender, maybe even 7 blenders, all at once, maybe in a store. You've all done blending. So no part of this is complicated, intellectually speaking. But if I ask you to express to me what on earth is in this vat, especially since now you have to express the taste test procedure as part of that recipe, you realize that your head is spinning a little bit. See, if we didn't have the taste test, then you could just say, well, actually, how much of each of these ingredients did we use? And you could just collapse the recipe down to, but why have all these different blenders? You could just collapse that down to effectively one blender. And then it's not a very interesting recipe. But with the taste testing, now it's something more complicated and convoluted. You have to write the whole thing out. And if I ask you to explain it to me, that is why you don't understand neural networks. Not because the individual bits are difficult, but because there is so much going on. They're building out these complicated recipes out of simple components. Let's see what it looks like in a more realistic setting. We have some binary features, light switches on and off, and we are going to combine them by taking a weighted sum. Now, this input doesn't have to be binary. Just for our example, we'll use some binary data to keep it simple. So here are our column headings, and our first row just says 1, 0, 0. We take a weighted sum, so our weights are numbers. And 0 times anything is 0, so ignore that. Our weighted sum result is 2. And then we are going to send it through an activation function to add some nonlinearity so that we won't just be able to collapse all the weighted sums down into a single simple weighted sum. So let's use one that we are comfortable and familiar with. How about Sigmoid Freud? So we'll use a Sigmoid activation function. So all we do is we find the 2, we put it in, we get 0.9. You don't have to use that activation function. You can go and find your favorite on a long list of them. The most popular one these days that the machine learning hipsters will tell you to use is ReLU, which sounds a little like an alien, I guess, but actually it's the one that I was describing with the taste test. It's just asking if the output, the weighted sum, is above a particular number, then keep that whole thing, and if it's below that number, then drop the whole thing. Actually, the hipsters probably wouldn't even go for ReLU. There's a whole variety of various activation functions. I think maybe a more hipstery thing would be the hyperbolic tangent or something else. So there's lots to choose from. What are you going to use in the end? Whatever is available in the implementation of the algorithm that you are working with. And if there are several options, what are you going to do? Try a few and see how it's going. But wait, there's more. We are going to take more weighted sums, and because we're tired of doing these calculations, we get the point already, we're going to pretend we did them, there you go, and we send them through our activation function as well. And then we do that again in the next layer, more weighted sums, more activation functions. And finally, our output, which we then turn into a 0 because it's closer to 0 than to 1. Again, you can all take weighted sums. You can all put a number through a simple function. That was not hard. But when you do this enough times and you stack enough of these operations together, if I ask you to write out the recipe that got you this final thing, well, that can make you dizzy. And if you don't believe me, to have real respect for neural networks, I would like you to play a game for homework called Do I Hate Cassie Yet? So here's how it works. For our simple neural network here, and I've even left a few things out, like bias terms and cool stuff like that, just for this simple setting. Write out the recipe in symbols, or you can fill in the values if you want. Write out the recipe that takes you from your benign binary inputs to the final output. What is the actual recipe over here? Not in terms of the operations, but in terms of mathematically with the logs and all that good stuff. Once you've written that out, add another layer with, again, 3 units in it. And see how much more writing it takes to go from this size with 2 hidden layers to 3 hidden layers. And you'll notice that your writing has more than doubled. But do we hate Cassie yet? If not, add another layer. And if you don't hate me yet after that, another layer. And another one, and if you get to 7, I'm super impressed. Because at some point you will be like, I have better things to do with my life. This is an annoying long recipe that I have no desire to read or interpret or look at. It consists of simple components, but it ends up being transformations of transformations of transformations. Very hard to read, very hard to write down. So you prefer to think simply in these individual components, but then when you're like, but what is actually going on? Very hard to see it. Even though each individual little piece is simple. That is why you don't understand neural networks, or rather why the recipe involved in neural networks is so difficult to think about and read and understand. But the operations that get you there, they are not so difficult. And TensorFlow makes you program in terms of these graphs and these operations rather than that recipe altogether. Now, why all these transformations? What do they get for you? Well, let's go back to our city planning example. With our historical buildings and our modern buildings, remember that example with our support vector machines? There, it was bad enough that we had all our red things all clustered in the center and the blue things around them. But we could do that whole kernel trick where we punch through the sheet and we transform it, making the dimensions higher, and then cutting it with the plane. That worked. But how are you going to take that approach to the spiral? Where are you going to punch it for this to work? Or maybe you want to try k nearest neighbors. How many nearest neighbors, and at what point will it break down and start finding neighbors that are from the wrong spiral? Or where do you want to do the decision tree here? All of our methods aren't doing very well for this example. Now, what those transformations do is they torture the underlying space so much that hopefully they pull it apart so that things got separated under all these crazy transformations, and boom, you can cut it again. And what that means is that you can solve problems like that one, where your data set is a bunch of pixel values. Where are you going to put a line through those pixel values to output cat, not cat? Now, you could go and maybe do some feature engineering by hand to go and first ask, is there something like ovals for eyes and 2 of them, and look for ears, and it's going to be a bit wobbly if you have this cat burrito with no ears. Instead, you could feed in a lot of data, and because this thing is so flexible and can do all these transformations itself, it will let you take advantage of those features without you having to explicitly go and find them yourself. This isn't free, though. There is a price here. Because this is such a complex recipe, we saw with the ideal body shape of the dataset that the more there is going on in the recipe, the more complex it is, the more features it uses, or the more transformations, the more length you're going to need, the more examples it will take to make it work. So this is very expensive, both in terms of how big your datasets need to be for this to be viable, and how much computing power it takes, because you see there's a lot of stuff going on. If you don't have a lot of data, you just simply might not be able to take advantage of this really powerful algorithm. Now, another thing is, when it says it exploits complex structure, and it finds those eyes and noses and so forth, this makes it sound like they're going to do that and show you what they're doing. They're not. Just behind the scenes might take advantage of stuff like edges, shapes, triangles, ovals, but you won't know what it's doing. So it'll be up to you to make sure that you really pick your test conditions carefully. Really think about the dataset. Which images are you going to use to make sure that this thing actually does work the way that you expect it to work? Check your dataset to make sure that there isn't something in there that is found instead of the label that you are looking for. Like in our earlier example where all of Cat 1 had radiator and all of Cat 2 didn't have radiator in the background. Make sure there isn't something special about your data, especially when you work with methods like this that don't lend themselves nicely to interpretability. It's really, really important to do profiling of your input data, profiling of your outputs, and think about what's going on there. Please do check, don't trust blindly. Now, what is there before we begin with this method? From the architecture, the settings that you set up how many layers are we going to use? Is it 1, 2, 3,000, whatever. You also choose how many units are in each layer, and it doesn't have to be the same number of units in each one. And you are going to choose the activation function that you'll use. So that's all there before you begin. From each data point, you get the actual values. So if this is a row in your spreadsheet, these are the column headings, and the first row has 1, 0, and 0 in it. And then as this flows through your network, the values inside the hidden layers are also determined by that particular example. And so as your network evolves and changes and learns, because it will learn from each individual data point in the simplest implementation, then you might have the same input values for 2 data points, but because the network has changed in between them, you might have different hidden layer activations. So that's all from the individual instances. So what is the part that we're learning? This is supposed to be machine learning, deep learning. What's the bit that's being learned? What do I hear from you? The weights, that mess. And I haven't even shown you everything here. I've left off the notion of bias units, which are going to add another 3 to these. I just wanted to keep it simple. But even with this oversimplified setting, what have we got? We've got 9 and 3, I can't count, 21 weights to deal with. For our calories example, we also had 3 features, carbs, proteins, and fats, and that was bad enough. We had 4 parameters to tinker with, and we were like, no way, just get on with it, optimization algorithm. We don't want to have to do this by hand. Look at this, 21 of them. Now imagine doing that by hand. Just take a moment. In comes a data point, and then which one are you going to change, in what order? In comes a data point. You'll be comparing the output that you want with the output that you got. You wanted a 1, it gave you a 0. Okay, which weight are we going to change? In what order? Turns out that optimizing those weights, before we die of boredom, is actually a challenge, and doing this by hand is just not going to work. So we're stuck unless we have an optimization algorithm that can do it quickly. And that is what the backpropagation algorithm is all about. For your purpose, backpropagation is the reason that you get solutions here, in this lifetime, rather than in the old age of the universe. You don't need to know much about it as practitioners because it's already implemented in those packages for you. You don't need to go reinvent the wheel. So even though it is part of day 1 of every neural networks course ever, if you're finding it tedious, you can just ignore that because it's already implemented. Just think of it as the reason that you don't have to wait forever for the results. I remember a fun moment where my friend who has a PhD in machine learning, who is a researcher, was saying, oh yeah, I have to go teach backpropagation tomorrow, so I can't go drinking because I have to go relearn it. Turns out you could be a career machine learning researcher and have entirely forgotten it, but somehow it's part of the hazing every time. So if you take a course and you're like, I'm not getting it and it seems annoying, do I have to fail out of the course or can I just ignore this one and hope it goes away? If you're going for how to be an applied person, you can probably get away without worrying about it too much. And let's see what's happening. We take an instance and we send it through the network just as we sent those numbers through earlier to get a label out on the other side, and we call that forward propagation. And then when we look at the label, we compare it with what the true answer was, and we see a mismatch. And of course, our first response is, whom do we blame? Well, to figure out where we should start making adjustments, we essentially propagate the effects, echo, influence of that error back through the network to find where and how much we should make the adjustments. That's what that backpropagation algorithm is doing for you. And if you do end up looking into it and you really want to know what it is mathematically, remember calculus? Remember the chain rule? Do you like the chain rule? I hope you do. After this, you'll like it out of Stockholm Syndrome. Backpropagation is just the chain rule a lot. And then the adjustment is made. And now you take your next instance, forward propagate it through, get the label, get the mismatch, back and forth, back and forth, back and forth, like sewing with a needle. And as those weights adjust, the solution becomes more and more of a good, sensible recipe for you. That's the simplest implementation. Now there are more interesting ones where you can train on many instances at once. Now you'll of course need to start with an initial selection of weights. So here's what not to do. Setting them all to 0. Anything times 0, you already know the answer. The punchline will be everything will be 0, no learning will happen. The next worst thing that you can do is set them all to the same number. Because fundamentally what this is doing is asking, well, whom do I blame? So you're looking for the most heinous looking culprit, and if they all look the same, then there's no one to blame. And then all of a sudden, no more learning happens, and you have a problem. And that's a kind of noob gotcha that happens also, either setting it yourself that way, or having it just accidentally end up learning itself into symmetry, and then there's no one to blame, and then all of a sudden learning stops, and you're like, what happened? And you go to your senior machine learning sensei, and they're like, oh, don't worry about it, just whack the TV one time, just restart it, and see if it's okay. And you're like, what is this black magic? This makes no sense. What, I just whack it and it works? Well, whack it with another selection of random weights, and hopefully you don't end up with that bad symmetric situation, and off we go. So symmetry is not your friend here. And if you end up in a situation with too much symmetry, then you might see that learning got stuck and isn't happening. Another reason it may stop behaving itself, stop learning, is maybe somewhere in there you're doing a lot of multiplication over a lot of layers, and you're multiplying fractions with fractions, and fractions multiplied with fractions, multiplied with fractions, multiplied with fractions become very small numbers, and eventually your computer can't tell the difference between them, and problems. Now, when it comes to this weights thing, the way to approach it is pick random starting weights. Yes, they are all wrong, but one of them is more wrong than the others, and then off we go. And I've got a footnote for you on some advice on how to set the weights. Okay, so the pros and cons of neural networks. The pros are that these complex transformations have so much flexibility that if everything else has failed, these still might succeed. They are best at fitting. So what's the con? What's best at fitting is also best at overfitting, exactly. And not just that. Remember the limbo, the overfitting limbo that you can get stuck in? Well, to work with these things takes more engineering effort and more computing resources. And so now you are riding this limbo merry-go-round, but you are riding it slowly, very slowly, and that is a painful existence. So you don't want to start with these if you have no reason to suspect that everything else is useless. You only want to be playing this game if you're pretty sure all the simplest stuff isn't going to work out for you. Now, how do we pick the architecture in practice? There's all kinds of advice out there on the internet, things like for input units, it's going to be your number of features, for output units, the number of label classes. For the hidden layers, start small. Why start small with the hidden layers? Overfitting. Even here, even within this class of algorithms, fewer hidden layers is a simpler algorithm than more hidden layers. And if you don't believe me, do that homework exercise of do I hate Cassie yet, and see just how much more complex the recipe gets as you add each layer. And hidden units, there's all kinds of crazy cool different architecture options. Some simple ones would be same number of units in every layer, so like a pipe, or like a triangle, a funnel, where you start big and you get fewer and fewer as you get to the solution. But there's many others. Why even listen to me when you can play with it yourself? You're like, I don't want to play with it myself because you just told me it's so much effort to try coding it up. We have a fun thing called TensorFlow Playground. You can click on that link, and then you go be the architect, and without writing a single line of code, you can go and see how different architectures affect the solution. So you can say, I want ++ 4 hidden layers, and I want to put 8 neurons in the first one, and I want to put 2 in the second one, and 3 in the third one, and so forth. And you're like, what activation function do I want? I want the hipster one, or I want the standard one, or whatever else. You take that from the drop-down, and you see how that affects your results on your output. And you'll see that there are going to be different scores for training and for testing. And you'll notice that you tend to do better, less loss, in the training than in the testing. Now, at the end of this section, neural networks might feel like a black box to you. And I hope that now you're okay with that. Now you understand why. There's a lot going on. Lots and lots and lots of operations. And so it's okay, don't worry about it. Don't try to read the recipe that comes out, especially if you have 1,000 layers and in each one there's 1,000 units. I mean, that's the sort of scale we're talking about with the big applications. Reading that recipe is going to make no sense at all to you. That's okay. Remember, at the end of the day, proof of the pudding is in the eating. So take the outputs. The output is the same as any other output. Doesn't matter what model made it. Compare it against the value you wanted and see how you're performing. So neural networks, try it first if. Yeah, there is a try it first section here, there are good reasons for this to be the first thing you try. Those good reasons are that you know everything else is not going to work because other people have already tried similar applications to yours and they've figured out that it's useless to try to attack it with a line or a tree or whatever else. I wouldn't try something else for images. If I'm doing image classification, I just go right to neural networks. I learn from the mistakes of others. Speech recognition, language translation is the same. Or if you have a lot of domain expertise and you know that the relationships are really complicated that you're dealing with, well, then you might want to go straight to here. So it's a good idea if your application is something similar to what other people do, to ask, hey, for data kind of like this, which algorithms tend to work out, and then you start with the simplest among those. Then, I'm kind of loath to say this, if you have a lot of data and you don't care how much computing costs, maybe in that situation you might also go right for it. But it is an expensive way to be lazy. Usually a little bit of analytics goes quite a long way to saving money and getting you decent solutions that are simple. All right, so thank you, that's it. You have survived the day, and with 30 minutes to spare, so 30 more minutes of alibi. And no one knows that you're goofing off, so enjoy. Thank you so much for being here, and I'm here for questions.